to take this concept of linear equations to its next level here, and that would be what's called systems of linear equations. Now, when we speak of a system of linear equations, we're really referring to two equations. I mean, in this case, two linear equations. So instead of just being given one equation, one linear equation, you're given two of them. And the idea is we're looking for a solution to the system. Now, that means if we have two linear equations, like two numbers add up to be 10, and those same two numbers have a difference of, say, 3, for example. Right? These two linear equations, and they are linear equations, constitute a system of linear equations. So that's all that means. You're just talking about two linear equations. Now, what we're looking for when we talk about a system of linear equations is we're looking for a solution to them. Now, a solution to a system of linear equations is an ordered pair that satisfies or works in both equations. Like if you take this first one, we saw x plus y equals 10, there's lots of solutions to this. X could be 5 and y could be 5. X could be 7 and y could be 3. X could be 8, y could be 2. Or x could be 2, y could be 8, etc. I mean, they go on all day. Pick two numbers that add up to be 10. There's infinitely many ordered pairs that satisfy that linear equation. Just as I could think of infinitely many that could satisfy this equation. For example, 7 comma 4, 6 comma 3, 2 comma negative 1. 2 minus a negative 1 is 3. Yeah, these are just some examples of, off the top of my head, two numbers that have a difference of 3. Well, when we talk about a system, we're looking for the ordered pair that satisfies both of these equations. So what ordered pair works in both? Now, the ones I have up here, I don't believe any of them work. And in fact, I don't think it's going to be pretty. I think the answer is 6.5 comma 3.5. 6.5 plus 3.5 does add up to be 10. 6.5 minus 3.5 is 3. This is the one ordered pair that would work in both equations. This would be what we call the solution to the system. It is an ordered pair that works in both. Right? So these work for that line. These work for that line. This is the only point that's common to both those, and that's what we're calling the solution to our system. Now, this kind of leads to how are we going to solve these, how are we going to solve these systems of equations? And the idea is, well, if they're lines, why don't we graph both the lines, and where the two lines cross, well, that should be where our solution lies. The solution to a system of equations, we can actually graph the two lines and see where they intersect. So the intersection point should be our solution. So we could have graphed this one and saw, and it wouldn't take much to graph them and see that. Let's start off with some friendlier ones. All right, so first method, we're going to learn to solve these systems. You probably remember, it's known as the graphing method. All right, so if they give you a system to solve, let's see, these kind of have to work out somewhat nice. So we'll go y equals 2/3 x minus 5. There's one equation, and y equals negative 2x plus 11. So negative 2/3 x minus 5 and negative 2x plus 11. Okay? You're asked to solve this system. You're looking for the ordered pair that works in both these equations. In other words, we're looking for where these two lines are going to intersect. So for lack of a better method, we're just going to literally graph these two lines out and see where they cross. So if you notice, this is kind of friendly. They're both in slope-intercept form, so they both should be very easy and ready to graph. And they are. First one has a y-intercept of negative 5. So we plot that, count out a slope of 2/3, which means from there up to right 3. Now, when you graph these, you only need 2 points, but the idea is we're looking for the intersection of these. That's the whole point. Where do these two lines cross? So it'd probably be wise to do several up to right 3s just to get more points on this line. Up to right 3. And we could also go down to left 3. We're looking for the intersection of these two. All right, so from this, let's see how straight of a line I can draw. We have a bunch of points that help me here. All right, there's our first line, y equals 2/3 x minus 5. Our second line, also in slope-intercept form, has a y-intercept of 11, so way up here, and a slope of -2, which we interpret as down to right 1, or, it doesn't matter, up to left 1. Now I know which one I prefer because the whole idea is I'm trying to draw closer to this line because I want to see where they cross. So I don't think it makes much sense to go up to left 1. That's getting away from this line. Let's go down to the right 1 and do it many, many times here until we actually hit this line. Hopefully it'll be a point we've already plotted. And bingo. Yep, right there. Took quite a bit to get to, but we made it. We graphed the two lines. These are all the points that satisfy the first or the second equation. These are all the points that satisfy the first equation. There is only one point that satisfies both equations, and it's right here at 6 for the x-coordinate, -1 for the y-coordinate. That is the solution to the system. This is called the graphing method. So literally you are just graphing these lines out and seeing where they intersect. Right? Let's take a second example. Okay, second example, I got 3x minus 5y equals -15. And y equals -2/5 x minus 2. Okay, so again, these two together constitute a system of linear equations. So, the idea is we're graphing these out just like we did on the previous two, and we're going to see where they intersect here. Okay, well, the first one, unfortunately, is not slope-intercept form. And I'm going to put it in slope-intercept form. So I'm solving this for the y variable. My first move would be to subtract 3x. So -3x minus 15. And then divide everything by -5. So -3 divided by -5 would be +3/5, and -15 divided by -5 would be +3. Okay, now they're both in slope-intercept form. Now I graph. So graphing this one, the y-intercept is 3. And then from there, I'm going to go up 3, right 5. Puts me there, if I'm correct. And just do that again. Up 3, right 1, 2, 3, 4, 5. And I could also go down 3, left 5. Let's do that one more time. 2, 3, 4, 5. It's not that I need these to draw a straight line, though it helps. What I'm doing is hopefully I'm going to have a point of intersection for one of these points I plotted, right, when I graph the second line, which is already slope-intercept form. So y-intercept is at -2. The slope is -2/5. So I could go down to right 5, or I could go up to left 5. I am going to go up to left 5 because that gets me closer to the other line. This one draws me further away. So let's go up 2 and left 5, and it only took 1. So, no sense plotting any more points. I have their intersection. The intersection looks like it's -5, 0. That's the solution to the system. Right. And that's basically how you solve a system of linear equations, by graphing. Not exactly the greatest method in the world, just for the fact that, graphing can be kind of difficult, particularly when it's not in slope-intercept form. Plus, accuracy can be somewhat of an issue. Okay, well, with that in mind, what we have to do is we have to take a look at the scenarios we can run into. The 3 different cases when you're given a system. because there are specific names for them. Okay, so for these, call them 3 cases. 3 cases. The first one, the name given is what we call consistent, and second word, independent. In fact, the 2 examples we just did would be called consistent and independent because what you're looking at, it's a system where the 2 lines intersect at one specific point. There is exactly one solution. So one solution, no more, no less. One solution, we call that system consistent and independent. Right? Second scenario that could happen, we could get a consistent and dependent. Consistent and dependent. Well, consistent and dependent would be something to where they turn out to be the same line. If they give you 2 linear equations, but those 2 linear equations are the exact same line, well, they're going to overlap everywhere possible. So you actually have, in that case, you would say infinitely many solutions, but consistent dependent would be the proper way to say it. And the third possibility is, what if the lines are parallel? Well, that's called inconsistent. Inconsistent, they gave you 2 linear equations, but doggone it, they were parallel. And the whole idea is, where do they intersect? If they're parallel, they don't intersect. Parallel. So there is no solution to that system. So know these terms. Now, we can tell without graphing if we're going to have this. You have different slopes. You can tell when you have inconsistent, same slope. Same slope, different y-intercepts, we'll say. And this, literally, is the same line. So you would have the same slope, but careful, they're not parallel. Same slope, they have the same y-intercept as well, which means they're the exact same line. So know the difference between these because they do ask you to classify these systems, and these are the classifications.